Welcome everyone to the inaugural of this seminar series. Having Professor Gopakumar as our first speaker, I will introduce him. Professor Gopakumar is currently director of the International Center for Theoretical Science, ICTS in Bangalore. He did his PhD at Princeton University under Nobel Prize winner Professor David Ross. Then being postdoc at Harvard University for some years. He was also a visiting long-term member at the Institute for Advanced Studies in Princeton from 2001 to 2004. He is the recipient of the ICTP Prize for Young Researchers, as well as several other international awards. His interests are in theoretical physics, mainly at the intersection of quantum field theory and string theory. His research tries to understand why string theory is a natural framework for describing a variety of phenomena, as we are going to see today. In particular, a lot of his research has focused on understanding the ADS-CFT correspondence. Other of his work on topological string theory led to applications to enumerative invariants, leading to the now so-called Gopakumar-Baffa invariants, which are very famous topological invariants in mathematics. It is a great honor to have Professor Gopakumar open this series of seminars by ICTP Physics Without Frontier and Physics Latam. Welcome once again, Professor Gopakumar.
Thanks very much, Danielle. Can you hear me well?
Yes.
Yeah, thank you. And I'm glad to be here for this very nice seminar series that Danielle and others have put together. Indeed, physics is something without frontiers, and I'm particularly happy that there is a large number of people who are joining from around the globe. And in particular, this is part of the physics Latin American series, which I'm sure there will be many very interesting talks to follow. And I'm sure it will enrich many of you who are attending it. So I will talk a bit about the problem, which in a sense I have been obsessed with for maybe many years now, more than 2 decades perhaps. So which is understanding gate string duality in some very first principles way, and in a sense trying to derive it. I will try to, I know that many of you do not have the background in string theory or perhaps even some aspects of quantum field theory. So I'll, at least in the first half of the talk, I will try to state things in a somewhat more general way, but for people who have a little more expertise, maybe you will see something in the second half of the talk, which is perhaps a little more in details. And but even if it gets a little technical, I would like to give everyone some overall flavor of some of the ideas in this topic, and try to convey how miraculous and magical this gate string duality is. So let me start. Okay. So did my slide change?
Yes.
Okay, great. And by the way, please either interrupt me at some point. I'll also try to pause from time to time for questions. Please interrupt me, or you can type your questions in the chat, and Danielle can also read them out. It's up to you. So right, Danielle, I mean, you will sort of look at the chat.
Yes, I will be taking care of it.
Okay, great. So this is roughly the plan of the talk. I'll try to explain a bit about what is gate string duality and why it is important. This I'll spend a little time because, again, many of you may not have seen some of this, but I won't be able to do justice to this topic. It is something that requires, I think, a whole course to really convey. So I will just give the broad picture. And then I will go a little bit more specifically, but still perhaps not too much into details, in which I will try to explain how a kind of a program to think of how strings can emerge from the kind of normal particle physics or description in terms of quantum field theory that we are used to. So in that sense, how I try to say it's like going from world lines to world sheets, where world lines are the space-time histories of particles, point-like particles, while world sheets are the space-time histories of a one-dimensional string, an extended string-like object. And then perhaps I will go into the more technical part in trying to explain how in some more recent work, how we have tried to understand this ADS-CFT correspondence, or this gauge string duality in the tensionless limit. And I'll try to show how we can, in some ways, in particular examples, go from fields to strings and from strings to fields. In this limit, I will explain what this tensionless limit roughly means. It will correspond to sort of a free or a nearly perturbatively free theory in the gauge theory side of the gauge string duality. So that's the rough plan, and I'll end with some quick outlook. So let's start by some general background. I think just since many of you are probably from very diverse levels of your studies, but you all probably know that quantum field theory and general relativity have been one of the main pillars of 20th century physics. They are both theoretical frameworks, very broad frameworks, which between them, in a sense, describe almost everything in the universe that we know about. So quantum field theory is the best description that we have for all the forces except gravity at the quantum level. If we want to understand electrodynamics or the strong interactions or the weak interactions, they're all described by a quantum field theory. In fact, by a specific class of quantum field theories called Yang-Mills theories or Yang-Mills gauge theories, because they generalize the Maxwell gauge theories that probably all of you have seen to a more general, what is called a non-abelian gauge theory. So these non-abelian gauge theories, these Yang-Mills theories with some matter fields, they describe the electromagnetic, the weak and the strong interactions, and it's been very experimentally very well tested. And general relativity, of course, is a very broad theory describing gravity in terms of the dynamics of space and time, in the terms of the geometry of space and time. And that has been a very good and experimentally now very well-tested description we have of the universe at the largest scale, or the macrocosmos, and we can follow the evolution of the universe almost very close to the Big Bang. I should say that quantum field theory is not only a description of some of these non-gravitational fundamental forces, but it is also now increasingly a framework that is able to capture complex phenomena and different phases of nature in statistical physics, in condensed matter physics, in fluid dynamics, and so on. So I want to stress that they're very broad frameworks. And I'll say a little more about each of these as we go along about these things, because part of the string theory effort is to bring these quantum field theory, general relativity together. So what is string theory? String theory is a very ambitious, it started off in a certain way, but it grew to become a very ambitious framework once again. So I want to kind of distinguish between a framework and a particular sort of electromagnetism is a very specific theory of which involves a specific field and a specific set of a specific field like the electric field, magnetic field, and some charged fields interacting with that. It's a very specific theory. But quantum field theory is a framework because it can have all kinds of describe all kinds of theories, including Maxwell's theory for electromagnetism, or the strong interactions, Yang-Mills theory with the SU3 gauge group. So so quantum field theory is a framework. String theory similarly is a framework, and it generalizes quantum field theory so that in a way which is able to capture gravitational interactions at the quantum level. And the way people initially realized this is that they use the fact that if you consider the excitations of a closed string that contains the graviton, or the quantum of gravity, which is a spin 2 object, as one of its lowest modes of excitation. And in particular, you could consider the interaction of these gravitons, because the interaction of strings themselves are given by these world sheets, as I mentioned earlier. So you can see on the left-hand side is sort of a world line description, which you may have seen in if you have studied Feynman diagrams. These are the Feynman diagrams of quantum field theory, which describe the world lines or the histories of particles as they interact with each other. In this case, maybe this is a photon, and these are some charged particles. And this is a history of their interaction. This, on the other hand, is in terms of world sheets, because you can see these strings at any given moment in time move and trace out a two-dimensional surface or a Riemann surface, and that the interaction is given in terms of these different kinds of Riemann surfaces. Just like for world lines, you draw different kinds of Feynman diagrams. Here you draw different kinds of world sheets, which might have these holes or handles in them. And so this diagram just shows, corresponding to, in a sense, it's a kind of a fattened version of these Feynman diagrams. But the remarkable thing is that once you describe the interactions of strings in terms of these world sheets, which generalize Feynman diagrams, you get a finite description of the quantum corrections to Einstein's equations. So Einstein's equations, if you naively try to use quantum field theory, you get infinities, and string theory helps to cure those infinities. But one thing I want you to take away is that like in quantum field theory, or like Feynman taught us in quantum mechanics, you have to sum. In quantum mechanics, you sum over all possible world lines, all possible Feynman diagrams. Here, you have to sum over all possible world sheets. But you can, just like in perturbation theory in Feynman diagrams, there's a small parameter which tells you that Feynman diagrams involving higher and higher loops are suppressed. Similarly, in string theory, Feynman diagrams involving higher and higher number of these holes or handles, which is called mathematically the genus, if you have taken some course in topology, the genus of this surface. There is a coupling called the string coupling, which suppresses the higher genus surfaces or world sheets compared to the ones like this, which don't have any handles or holes in them. And this coupling constant is what we would interpret as the Newton's constant, and that is what tells you, in a sense, that gravity is part of the description of in a string theory. It comes out very naturally. So that's one thing I just want you to, if you have not seen any string theory before, just remember that in some ways, the prescription to study interactions of strings is a generalization of what you study for particles. It just involves worldsheets, and worldsheets which have many handles or holes have to be weighted with the factors of this string coupling, or GS, the whole square, which is proportional to the Newton's constant. Okay. So before I talk about gauge string duality, I just very quickly was telling you about gauge theory, string theory, and the frameworks of quantum field theory and general relativity. But are there any quick questions? If there are any quick questions, I can answer them right now. Okay, so I'm assuming it's okay. So let me start with gauge string duality. By the way, as I said, please feel free to write on the chat, and Daniel will stop me at the appropriate time and tell me. So you had the string theory, which was a very good description for quantum gravity. It seemed to be a generalization, as I said, of the framework of quantum field theory. But what people realized is that, and this was actually the work, brilliant work of Juan Maldacena, originally from Argentina, and a classmate of mine, actually, it so happens. But so he showed, or he realized that the consistency of string theory requires an equivalence between string theories in certain class of spacetimes and gauge theories on the boundary of that spacetime. So I should explain a little bit about what these spacetimes are. They are what are called anti-de Sitter, or ADS spacetimes, and ADS is just anti-de Sitter space is essentially sort of a physicist term for a space-time which mathematicians think of as hyperbolic space-time, namely things with constant negative curvature. And that's why in this diagram has been drawn with this anti-de Sitter space is represented by a solid cylinder. So a cylinder in which the interior is part of the space-time. In fact, time you can think of as the vertical axis of the cylinder, and all the horizontal cross sections are spatial slices. And in these spatial slices, the geometry is hyperbolic. Actually, the whole space-time geometry is hyperbolic, but in particular, in these spatial slices, you see these hyperbolic pictures of Escher, which is kind of showing that these are spacetimes with negative curvature. So in this class of spacetime, so anti-de Sitter space can be represented or conformally represented by the solid cylinder. So a solid cylinder has a boundary, and the boundary is what you might think of as the surface of the cylinder. And the surface of the cylinder is one lower dimensional boundary, or a conformal boundary, as it is called. And you can consider a quantum field theory on this boundary, and this remarkable statement of gauge string duality is the equivalence between class of gauge theories on living on this boundary, which is, if say in some d-dimensional boundary of this cylinder, and that is completely equivalent to the quantum gravity or string theory in the inside of that cylinder. So think of like a Coke can or something. It's as if by reading everything or knowing everything on the outside of the can, you're able to reconstruct everything inside the Coke can. So that's the picture over here. And the kind of gauge theories that we will be considering are non-abelian gauge theories, so Yang-Mills theories, like the ones that appear in the standard model. So in particular, these will have a gauge group, which is the group SUN or UN, group of n by n unitary matrices. and you will be considering the large N limit, where there are some remarkable simplifications of gauge theories. So these large N gauge theories on the cylinder, the claim is that they are dual to, or at least for a class of large N gauge theories, which are conformal also. That means they have an extra conformal invariance, which goes beyond the Poincaré invariance or Lorentz invariance. They have an additional scaling kind of a symmetry. This conformal theories, or conformal field theories, or CFTs as they are called, are dual or capture everything about the quantum gravity that's on the inside. So what does this duality really mean? What does it translate to? It means that if you ask a question about the quantum field theory on the boundary, it is equivalent to asking a certain question in the dual string theory or gravity, and vice versa. So there is a dictionary between the so-called bulk, which is the inside of the Coke can, and the boundary, which is the surface of the Coke can. And there's a holographic dictionary because it relates observables in the d-dimensional boundary of this, which described by a CFT. That's what the CFT subscript D represents. And the claim is that is dual to the anti-de Sitter spacetime in D+1, the interior, the bulk. So there is a dictionary, and I will tell you a little more about this dictionary as we go along. So this is very remarkable because you can translate questions about quantum gravity into questions in quantum field theory, which you understand better, which don't have anything to do with gravity. These are Yang-Mills gauge theories, which have nothing to do with gravity, but yet they are able to, in fact, even reproduce things, facts about Einstein's gravity, or vice versa. You can use it in the other direction. So this arrow goes both ways here. The questions in quantum field theory can tell you about things in gravity, or vice versa. Gravity can tell you about things in quantum field theory. And moreover, it can tell you non-trivial things, new things about quantum field theory from gravity, or new things about string theory or gravity from quantum field theory. And why is that? And that was one of the central insights of Maldacena, that it's a duality which is relates a weakly or highly curved ADS. So it relates a weakly curved or small curvature ADS to a strong coupling quantum field theory, and vice versa, a highly curved ADS to a weak coupling quantum field theory. And I will elaborate on this a little more. So, but just this statement itself is quite remarkable because it's telling you that a weakly curved ADS, that means where the curvature is very small, that's something that you can describe very well by Einstein's equations. When curvatures are small compared to, say, the Planck scale or the so-called tension of the string, then you can describe things very well by anti-de Sitter space, and that is equivalent to a strongly interacting quantum field theory, where you can't use normal perturbative methods of quantum field theory. Whereas in the other limit, if you have a highly curved ADS, that's very difficult to describe using Einstein's theory because the curvatures are comparable to the Planck scale, and therefore there will be corrections to Einstein's theory. That is described by something you all study in quantum field theory graduate courses, namely using weak coupling quantum field theory or perturbative quantum field theory. So it's remarkable that you can learn about string theory or quantum field theory in a regime which you can normally not easily understand using this two-way dictionary between the two sides. Okay, any quick questions before I elaborate on some more of these statements? Okay, so
sir.
Yes.
So I have a question. You see, means if you apply string theory itself is renormalized theory. But when you apply quantum field theory to the gravity, means the things become divergent.
Yes.
So means how this dictionary works? Means suppose you are going
So
to dictionary.
yes. So this quantum field theory, we are not applying to gravity. It's this quantum field theory, which is on the boundary in this dictionary. The dual description, the CFT on this d-dimensional boundary that I mentioned, is a pure gauge theory, which is in which all the divergences that are there are, so to say, renormalizable. It's a completely well-defined gauge theory at the perturbative, non-perturbative level. So in this CFT, there's no gravity. That's the miraculous thing. It seems to be in terms of a completely different set of variables, in terms of some UN by UN gauge fields, meaning matrices, N by N gauge field matrices, which have nothing to do with gravity, but seemingly, but you can translate questions, and I will tell you a little bit about that. Translate the questions about the gravity in terms of questions in this quantum field theory. And the string theory, you are indeed right that it gives you finite answers, and those will be reproduced by the finite answers given by the quantum field theory. Does that answer your question?
Yeah, I got it.
Okay.
I have another one. Oh, sorry.
Yes.
So, hello. So, is there a specific type of force that the gravity in the ADS is corresponding to, like in the boundary CFT?
In the limit of a weakly curved antidecitor, it is described by just Einstein's gravity theory plus some additional fields, a few additional fields. But in general, it's given by a string theory, which is a closed string theory, as they say, which describes not only gravity, but several other higher spin fields, higher spin forces and their interactions. So the string theory describes inside in the antidecitor, it is describing essentially gravity plus some additional stringy forces.
I know. What I mean is like the gravity component of in the ADS is corresponding to something in the CFT, right? So is
Yes.
there a specific type of force that it is corresponding to?
Okay, so it's not a specific, so that's the interesting thing here, that it's not a force in the sense of the force picture that you see in the inside of the gravity. Corresponds to something like, it's a correlator that you compute in the field theory using just the forces, the gauge forces of the field theory. It's just one of the particular gauge field interactions. So a slightly better way to say it is, in every quantum field theory, there is an operator called the stress tensor. So it's the interactions of the stress tensor operator in the field theory, or the energy momentum tensor in the field theory, which capture the interaction between gravitons in the antidecitor spacetime. So if you wish, a scattering of gravity particles is described in terms of correlation function in the field theory involving the energy momentum tensor. And more general objects like black holes inside antidecitor spacetime, inside the bulk spacetime, are described in terms of the gauge theory at finite temperature, some excited states in the gauge theory. So all the gravitational phenomena is mirrored in the gauge theory, but in a very non-trivial way, because it is not a local mapping, and it cannot be, because you're mapping a d+1 dimensional spacetime, all the information about it, onto a d-dimensional boundary.
Okay, thanks.
Are there some correspondence for the gauge symmetries in the
For the gauge
string theory?
symmetry?
Yeah.
Yeah, that's a very good question. Interestingly, not, because the gauge symmetries in the field theory are viewed as essentially a convenient description. It's not a real symmetry. It is not an actual symmetry like Lorentz symmetry or rotational symmetry or translational symmetry, which lead to conserved quantities. So the gauge, actually, I like to use the word gauge invariance. A gauge invariant description is just the statement that you are making the theory, writing it in terms of some extra variables in which has some additional invariance, which is a convenient way to describe the theory. So electromagnetism, you can choose to write the theory in terms of the vector potential, which has certain gauge transformation, but all physical quantities like the electric field are gauge invariant. So you do not really, so the gauge, the description with the gauge freedom in it is a kind of a convenient description. It is not a fundamentally symmetry of the theory. And therefore, the gauge, therefore, when you, in this dictionary, what you compute are objects involving gauge invariant quantities like the electric field or the magnetic field or generalizations of those. So you never see the underlying gauge freedom. You are always looking at things which are invariant under this gauge transformations.
And that happens with other invariants or symmetries? Or?
No, other symmetries like the global symmetry. So people distinguish between global symmetries like Lorentz symmetry, rotational symmetry, translation symmetry. These are global symmetries. They correspond to conserved charges like angular momentum or momentum and so on, or even the global part of the gauge symmetry, which corresponds to the electric charge. But that's just the global part, the piece independent of any space-time coordinates. So those global symmetries have to be present on both sides if this equivalence is to work, because they that all the states in your theory have the property that they carry some charge under this, they carry some momentum or angular momentum or spin, whatever you want to call it, or maybe electric charge. And those states there must be states in whichever description must have these same quantum numbers. So global symmetries lead to conserved charges, which lead to certain quantum numbers for every state. Labeling every quantum state, and that must be preserved in the two theories. In fact, so somehow, so in this correspondence that I was telling you, will tell you a little more about, there is a equivalence of the Hilbert spaces of both sides. Both sides are quantum theories that are described in terms of a Hilbert space, and the two Hilbert spaces are the same. So any charge, any global conserved charge or quantum number carried by one on one side of the duality must be there present on the other side. And you actually see this. So in like the conformal symmetry is part of what is called the global anti de Sitter symmetry. Anti de Sitter spacetime is this hyperbolic spacetime. It has a global symmetry, which is the same as that of the conformal group on the boundary, SO2, D, in this particular case. So like four-dimensional conformal symmetry is the group SO2, 4, which contains the Lorentz group SO1, 3 and translation, but also additional conformal generators. So these this SO2, D is the is a global symmetry that is present on both the Hilbert, in the Hilbert space on the boundary theory, and also in the bulk theory. So yes, so for the global symmetries, there is a complete equivalence because of this equivalence of the Hilbert spaces. Okay, good. I'm glad people are asking questions because that's the best way to sort of follow things. So as I was saying, there's an equivalence of the Hilbert spaces on both sides. Operators on the boundary theory, you consider gauge invariant operators to be more precise. On the boundary conformal field theory, they correspond to states in the bulk theory. In particular, this holographic dictionary, let me just tell you a few entries in this dictionary. The first few entries, you might want to understand what corresponds to the energy in the bulk spacetime, and that is translated interestingly into the dimensions of the various operators. So quantum field theory, you have the fields and their composites lead to various operators, the operator valued fields in the quantum field theory. These have a certain dimension. It is not necessarily the naive engineering dimension that you have. If you have taken a course in quantum field theory, you might have seen that they have something called an anomalous dimension, which is about how they really transform under scaling or conformal symmetry. And these dimensions of operators are what correspond to the energies in the bulk spacetime. And so that's the first entry. This you can think of also as a relation between the 2-point functions of operators, or correlation functions involving two operators in the CFT are related to the energies in the bulk spacetime. So from those 2-point functions, you can read off the anomalous dimensions and translate that into an energy in spacetime. And similarly, a 3-point function of correlators that corresponds to a cubic interaction in the bulk of gravity plus the kind of tower of particles that are there in string theory. So, and so on. The 4-point correlators, correlators means correlation functions of 4 say 4-point function is of 4 operators, and those would correspond to some kind of quartic interactions or exchange interactions in the bulk theory. So that's part of the dictionary. Another very important part of the dictionary is what basically I mentioned at the end of the last slide. It's the relation between the parameters on both sides of the theory. So there are 2 important parameters on both the CFT side and on the string theory side, and they are related in a very interesting way. So let me start with the field theory. There is something which is often denoted by lambda, which is essentially the Yang-Mills coupling square times n. N is this rank of the gauge group, the UN gauge theory that I mentioned. So this combination G Yang-Mills square n, which is sometimes called the 't Hooft coupling or lambda, is a very natural combination, which is what governs the perturbative expansion of Feynman diagrams in a large N gauge theory. So this is a very natural combination on the gauge theory side, on the UN gauge theory side. And that translates to the same parameter lambda is actually, or power of lambda is proportional to the radius of curvature of the ADS. So it's a measure of the size of the ADS. So very so I'll say how, but at the moment, just take this in that the radius of the ADS corresponds to this parameter lambda, and this as when lambda is very large, this radius is very large. When lambda is very small, this radius is very small. Okay, so that's one entry in the dictionary. Another is a very important one is to do with the n itself, the number n. And here, this is where the old ideas of Toft about the large N expansion of gauge theories comes in. He realized that 1 over N is a parameter that you have in a gauge theory, and in which you can do an expansion for large N, can do an expansion in powers of 1 over N of your theory, provided you keep this combination G Yang0 square N or lambda fixed. Then you can organize your Feynman diagrams in a very interesting way, which I will talk about, in powers of 1 over N. So there are 2 parameters in your theory. I mean, normally in a Yang-Mills theory, you only think of G Yang-Mills square as the parameter, but now there's this extra N. So you form this combination lambda, G Yang-Mills square times N, and you think of N or lambda over N, and that second combination is what corresponds to the other parameter in the string theory side, which is this G subscript S, G, which is the string coupling that I mentioned earlier. That is the, which is the square of that was proportional to Newton's constant, like I said earlier, and that is what governs the number of, that's what you use to weight the world sheets with more and more holes or handles or higher genus world sheets. So this parameter on this, the 1 over N expansion, when you take this as the parameter for a large N expansion, that effectively translates, you see here, to the perturbative expansion. When N is very large, then and lambda is fixed, then lambda over N is small, and that is so that an expansion in this parameter is what would correspond to the string perturbation expansion, or an expansion in terms of world sheets of higher and higher genus. So that's these are the 2 important entries in the dictionary. Strictly speaking, this entry here is what, I mean, these entries I have written for the simplest case of string theory on ADS 5 times now the higher times the higher dimensional sphere. But right now, let's focus on the anti-de Sitter spacetime. So in ADS 5, which is dual to a 4-dimensional Yang-Mills theory or a super Yang-Mills theory, that is given by the dictionary is given by what I've written. It's more or less the same in other cases, but just to give you a concrete example. And this dictionary tells you immediately, tells you the statement that I made in the last slide, which is about it being a strong weak coupling duality or an equivalence. So strongly interacting quantum field theory has the coupling very large. This is the meaning of this parameter is the sort of measures the strength of the Yang-Mills interaction. And when this is much greater than 1, you say it's a strongly interacting quantum field theory. But you see from this dictionary that if lambda is much, much greater than 1, then the radius of ADS is also much, much greater than 1. And this being much, much greater than 1 is the radius being much, much greater than 1 is a statement that the curvature is very small. And therefore, when the curvature is very small in the natural units that you measure it in, you can use Einstein's gravity. You need not worry about additional corrections, so-called higher derivative corrections, when the radius is very large. So this is a regime where you can use Einstein's gravity description, the usual Einstein's equations, to describe something that you otherwise find very difficult to study, namely a strongly interacting quantum field theory, for which we have very few techniques. All our perturbative field theory techniques work only for weak coupling. But interestingly, when you, in that regime where you are this weakly interacting quantum field theory, where the coupling is very small, that you see corresponds to the radius being very small. And radius being very small corresponds to a high curvature. Just think of a very small sphere, it's highly curved, right? Or a small circle is much highly curved, compared to a very large circle or a sphere. So in any case, that is a regime where you don't know how to describe the bulk theory, the gravity theory, at least in terms of Einstein's theory. And it's a regime which you would call the stringy geometric regime. And that's where, so that there, the quantum field theory can help you in understanding about the stringy regime, whereas here, the Einstein theory can help you understand about the strongly interacting QFT. So this is the remarkable equivalence that because of this duality, when you don't know one side very well, you can use the other side to learn about this one. And this works between the quantum field theory and the gravity. So even if you don't take away very much more from the talk, please take this very important statement about gauge string duality, this holographic duality away. Any questions? Yes, please.
Thanks. Hi. I have a question about the quantum equivalence of both Hilbert spaces. So when you mentioned that operators in the boundary are dual to states in the bulk, that these operators acting on the vacuum of the boundary, right?
Yes, there is a what is in the boundary. There is something called a state operator correspondence in any CFD boundary. CFD, there's a way in which you can the operators acting on the vacuum can be create certain states in the boundary theory, and those correspond to the states in the bulk theory. Yes.
Okay, and that like correspondence means that there is some kind of correspondence between the vacuum of both theories, or the
the vacuum of the field theory is where you have not excited. There's a unique ground state that corresponds to empty ADS space where you have not excited any bulk particles like gravitons or anything else. So you're just looking at the empty ADS space time.
Okay, thanks.
Okay, welcome. All right. So let me go on. Well, I think I'm going very slow, but anyway, never mind. I think the important point is to get across some of the important ideas. So now, why is this a big deal? Well, I think I've already given you some sense for why it's a big deal, but let me elaborate further. So firstly, from the general relativity side, it gives a very concrete model for what a quantum gravity description can look like, at least for this class of spacetime, this anti-de Sitter, or more exactly asymptotically anti-de Sitter spacetimes. And it realizes here an old idea going back to 't Hooft and Susskind and so on of holography, that the microscopic degrees of freedom of a gravity theory are captured in a holographic screen or one lower dimensional boundary. And the remarkable insight here, which had not been guessed earlier, that this holographic description is in terms of a familiar quantum field theory. So in some sense, you come back full circle. People thought that quantum field theories can't be used for describing gravity, because if you try to treat gravity as a quantum field theory and quantize it, you run into all kinds of problems, infinities, various things. But you've now come back with a twist, saying at least for this class of spacetimes, you can describe gravity in terms of a quantum field theory, except it's a very different quantum field theory, which seemingly doesn't have anything to do with gravity. It's a gauge theory in terms of some gauge degrees of freedom, very different degrees of freedom from your original gravity degrees of freedom. It is not even living in the same spacetime, it's living on the boundary of that spacetime in one lower dimension. It has therefore far fewer degrees of freedom than that of the bulk spacetime. So it's a very, so it's sort of come back with a very interesting twist. And from the quantum field theory side, also, it's quite remarkable because it tells you that many quantum field theories in the strongly coupled, for instance, in the strongly interacting regime can be described in terms of gravitational physics. And you can, in that regime, which is, as I said, strong coupling in the field theory is a low curvature and therefore Einstein's equations, you can solve Einstein's equations to learn a classical Einstein equations, tell you about a very highly quantum regime of the gauge theory. And this, I think, is, and for me, has been one of the very interesting motivating factors, that it realizes very old ideas, in some ways going back to Faraday and Maxwell, how you can think of the flux lines of gauge theories as strings, that really the strings that we are talking about here are emerging from the gauge theory in terms of the lines of flux. So Faraday tried to think, and Maxwell tried to make precise the idea that maybe you can try to describe gauge theory not in terms of fields, but in terms of the lines of flux. In some ways, it's a realization of that picture, and I have a quotation from Dirac much before string theory was invented, which sort of goes in that direction. But anyway, that's I think a very remarkable feature of this duality, that it realizes in a very precise way how strings can emerge from gauge theories. So strings are not just some things that you think of one day, oh, I don't like point-like particles, so I'll think of some one-dimensional strings. No, it's not like that. The strings are arising from the framework of quantum field theory itself. The quantum field theory itself tells you that sometimes, in some cases, string-like degrees of freedom are the most natural descriptions or the physical descriptions of the theory. For those of you who are here from a maths background, maybe you have heard of something called the Langlands correspondence. I just want to say that this is such a very big, it's in the flavor, the grandeur, and the scope of this correspondence, this ADS-CFT, or more generally gauge string correspondences like the Langlands correspondence, sort of unites and very different areas of theoretical physics in a remarkable way, in a way which allows you to learn about both sides of that correspondence. Okay, so and ADS-CFT has had a major impact in many areas of theoretical physics and also mathematics. But just to list a few applications in high energy physics, it inspired the Randall-Sundram and other related models. It inspired many interesting ideas about scattering amplitudes of gauge theories at strong coupling, going to the work of Byrne-Dixon and Smirnov, I think. In QCD, it gave rise to a whole class of effective field theories, and there's a whole industry of people who try to model QCD using anti-de Sitter space-time-like geometries. It has helped at finite temperature phases of QCD, like the quark-gluon plasma, in understanding properties about what the strongly interacting plasma might be like, and which led to interesting statements about the viscosity to entropy ratio and the so-called fluid gravity correspondence. In cosmology, also, it has led to these different scenarios, KKLT, LBS, etc., and swampland related, in condensed matter physics and quantum information. Also, it has had major impact in some of these topics that I mentioned. So it has really been very wide in its impact. So if you are going to specialize in many of these areas of theoretical physics, it's good to have at least a certain acquaintance with the ADS-CFT correspondence. Okay, so that brings me to the first part of my talk, the end of the first part of my talk, but and I see that it's almost 1 hour. So Danielle, I mean, tell me, how long should I go on? And I'll sort of tailor it accordingly.
I think it's meant to finish like in 30 minutes.
Okay, so maybe I'll try to talk for another 15 minutes and then keep 15 more minutes for questions at the end. Does that sound?
as you like. We can also go maybe 10 minutes more if you need to cover something extra. It's up to
Yeah,
you. It's fine.
I mean, as I said, I don't need to cover everything that I have because especially the more technical parts. But let me go ahead and then we'll see, depending on how the questions go and so on. So let me now try to say a little bit about the idea of deriving ADS-CFT. So I hopefully have convinced you that this is something very fundamental to understand from a first principle point of view. But you can ask the question, how does a quantum field theory become a theory of strings? I mean, how exactly does that happen? And Maldacena was guided by a certain intuition from string theory, which tells you, which I've tried to capture in this cartoon here, which is something called open-closed string duality, which I can say many more things about, but it arises because of the kind of remarkable thing about in string theory, you find these objects called D-branes or Dirichlet branes. They are basically like defects in space-time on which strings can end. So strings come in two varieties. There are open strings, which have two endpoints. So that's like a piece of string, like a thread with two endpoints, or rope with two endpoints. Or you can have a closed string, which doesn't have any endpoints, and it's more like a rubber band or a hoop. And one of the remarkable things about D-branes is that they have two descriptions. One in the open string description in terms of things on which the endpoints of the strings can end, and a closed string description because these are kind of defects in space-time, meaning the strings can end on some objects with some codimension. They are of lower, they can be sometimes of the same dimension, but often they are of lower dimension compared to the full space-time in which the closed strings move. The open strings can sometimes be restricted to lie on these defects. But the D-branes have two roles, one as open strings ending on them, and the second as, because they are defects in the space-time, they carry actually energy and momentum, and therefore are sources for closed strings. Because anything that carries energy and momentum, gravitates, and graviton is one of the closed string modes, and therefore the D-branes can be sort of on the one hand, they source gravity and therefore kind of change the space-time around them. But on the other hand, they can be also viewed as open strings. And that's how this duality arises, because amongst the modes of excitations of the open strings are the Yang-Mills degrees of freedom, gauge degrees of the conventional gauge theories, Yang-Mills theories. Whereas in the closed string description, you get the graviton, because the closed string, the simplest excitation is the graviton. The open string, the simplest excitation is the gauge field. And in fact, you can get UN gauge fields because you can have N D-branes and then you get a UN gauge theory. So these gauge theory diagrams are therefore open string diagrams, and I've tried to draw some open string world sheets here. Our open string world sheet is a two-dimensional surface which has boundaries, because boundaries correspond to the end where the endpoints of the string are. In the string endpoint, if you think of it in space-time, it will trace a one-dimensional trajectory because it's just the endpoint of the string, whereas the whole string will trace a two-dimensional trajectory. The endpoint can trace a one-dimensional trajectory, and these holes are in some sense the reflection of that one-dimensional endpoint, and these correspond to these actually you can show just our gauge, these open string diagrams are really the Feynman diagrams of a gauge theory, of a large N gauge theory. And the statement about this open closed string duality of D-branes is that in some ways, if you kind of sum over all the Feynman diagrams and so on, that's what the left-hand side of this cartoon are supposed to represent, then some magic happens and the holes go away and you get a closed string world sheet, which doesn't have any holes, but has the closed string interactions in it. This is very difficult to see when the coupling is very large, but you might hope to see this when the coupling is very small, when this 't Hooft coupling lambda, which is the same as actually G Yang-Mills square N or G string N. When this is small, you might hope to be able to show this explicitly and in some ways derive gauge string dualities by saying how Feynman diagrams, the left-hand side, become the closed string world sheet. So a few things ago, I made this distinction between Feynman diagrams here and these closed string world sheets here or in this picture. But now I want to say that open closed string duality tells you there's an interesting relation between the field theory Feynman diagrams and these closed string Feynman diagrams. Okay, so but before I tell you a little more, let me give a little motivation for why you might want to derive ADS-CFT or understand it. Because firstly, it's not for some mathematical rigor or trying to derive it because you want to kind of you want to satisfy some mathematical standards. It's actually driven by a physics reason because you want to go beyond the particular corners that we understand, and we really want to uncover the sort of the inner workings, the inner wheels of this duality. What is it that makes it tick? And you don't really understand it yet. I mean, this whole duality beyond certain corners, because the stringy ADS-CFT, when you go beyond the Einstein's theory of when the curvatures are very small, as I said, you can describe Einstein's theory, but when the couplings are of order 1, that means the curvature is of order 1, then you don't know how to describe things in the field theory, and at the same time you can't describe it purely in terms of Einstein's theory, but you can try to describe in terms of a string theory in the anti-de Sitter spacetime, which you would like to get a handle on. And it is in these regimes that if you want to describe a string description for QCD, as I was hinting at earlier, people all had felt that gauge theories can be described in terms of strings. And in something like QCD or maybe even other strongly correlated systems, you might want to have a stringy description, not an Einstein theory description, a stringy description when couplings are of order 1. How can you give a string description for QCD? And more generally, when can quantum field theories really reassemble into string theories, or when can strings emerge from quantum field theories, string-like excitations? So you'd like to know when, because many of the examples are currently ones which involve something called supersymmetry, and we would like to go beyond those examples and therefore kind of demystify this from this holography, this connection that I said might have seemed very mysterious to you, and that is not a surprise because it's still very mysterious to everyone, but you want to demystify it. That's the job of a physicist, to kind of demystify miracles, because you want to see how things really work. So that's sort of the philosophy. And these two parameters that I mentioned over here, there's a way I like to represent them in terms of sort of, so there was on the one hand, let me remind you what the two parameters were. On the horizontal axis, there was this parameter lambda, which was the Toft coupling, G Young-Mills square n. So that is also proportional, some power of it is proportional to the radius of the ADS, as I mentioned. And this is the weak coupling regime, lambda going to 0. This is the strong coupling regime, lambda becoming very large, but that corresponds to the radius becoming large or curvature small. So that's the horizontal axis, the parameter lambda, or equivalently the radius of the ADS. The vertical axis is 1 over n, which, as I said, is a parameter in the large N expansion and the large N gates theories, which translates to this string expansion, the expansion in genus, or the perturbative string expansion parameter GS, which is like Newton's constant, essentially, square root of the Newton's constant. So this is the vertical axis. And in a way, a lot of the work has been in this right-hand bottom corner, where you take n very large, or you don't consider so many of the stringy effects or the quantum effects on this side. So this regime is what you might call the fully quantum string theory. But GS very small, or n going to infinity, is a regime where you can talk about strings in the classical level. And if you further specialize to this corner, you can think of not only classical string theory, but classical gravity theory, because the curvatures are very small. And so this has been the kind of lamppost we have been under a lot of the time. But at least you can move along this axis. And there's another interesting lamppost on this side as well, which is that involving perturbative quantum field theories, where the coupling is very small. The Young-Mills coupling is very small. You understand the field theory very well, even if you may not understand the string theory. So that's an opportunity. And then you might hope to try to go from here and connect to this side, and eventually even go into this regime. So as I said here, most of the work has been in this Einstein gravity limit, because it has been tractable, and you've gained enormous insight into strongly coupled quantum field theories where the coupling is very large, purely from classical gravity. But I want to shift the focus a bit to this other side, where we understand the field theory, but we don't really understand the bulk theory, because it's stringy anti de Sitter spacetime. It's a space here. This is the regime where the radius of the anti de Sitter spacetime is stringy, is of the string scale, which is related. It's just maybe a couple of orders of magnitude smaller than the Planck scale. So that regime is where lambda goes to 0, is something you often call the highly curved ADS, or sometimes even the tensionless limit, because the string tension is the inverse of the string scale, length scale. And you can say that effectively it's like a string which is with 0 tension. So that's the regime we will focus on. And let me say now a little bit about what I mean by a derivation. So this is maybe looks a little intimidating, frightening, but this is in a way elaboration of that earlier dictionary that I was mentioning, now involving the left-hand side is the field theory, the right-hand side is the string theory. Now, what are the things on the left-hand side? They are operators. They are what are called correlation functions of operators. In this case, I've taken n operators at x1, x2, xn. These are the positions of the on the boundary of the field theory, which you can actually take to be that I showed you a cylinder, but you can actually take it also to be a sphere conformally. there are various labels which you can forget about that are associated to the operators, because there are many operators in a quantum field theory, come in many species, and they have many dimensions and so on. So you have an infinite tower of operators. Those correspond to the different states. These are technically what are called single trace operators, and they are, of course, gauge invariant. I mentioned earlier, you consider only quantities in the field theory which are invariant under the gauge transformations. So so the left-hand side is a correlator, and you consider it in a large N gauge theory. That's the capital N, and you expand it out in this 1/n expansion and pick out the piece. There's a piece of it where in which essentially has a power which is n to the 2 minus 2g. So when you do a 1/n expansion in the you get in powers of 1/n square, and the gth term in that expansion, if you take that, the statement about the ADS-CFT duality is the equivalence to this correlator. This correlator is that of a string theory. It's a scattering amplitude in a string theory. And again, don't let the terms intimidate you or frighten you. It's basically the way in which you would compute on a world sheet of a string theory in which you insert the operators at some positions Z1 to Zn, and you consider a world sheet with of the same genus G. There's number of handles that appears here, and with n punctures. So you consider Riemann surface or a two-dimensional surface with n points, Z1 to Zn, and with G handles. And you compute some quantity in a two-dimensional field theory on that Riemann surface. That's the prescription of string theory. That's the more technical prescription of string theory. And you then have to integrate or sum over all the world sheets, the different space-time world sheets you can have. And that corresponds to this so-called integral over the moduli space of these surfaces. So anyhow, even if the details are not escape you, what you just remember is that there is an endpoint function, little n function, and the field theory is dual to certain scattering amplitude in the string theory, which you know, which there is a in principle well-defined way to compute, and this requires a certain dictionary between the states, and that's the operators in the field theory and corresponding states in the bulk. That's this dictionary again, written out in a little more in a little more elaborate form. So the important thing I want to stress is that both sides have well-defined quantities. So the left-hand side is a quantum field theory correlator. It's a mathematically well-posed question to ask whether this object here that you can compute for different operators for different positions as a function of x1 to xn for a given genus G, does that agree with this right-hand side, which can be computed using what is called a two-dimensional conformal field theory on the world sheet of the string, which is the prescription you normally have to compute a string amplitude. So this is in principle, a mathematically well-posed question. And what I would like to have as a derivation, but I won't have the time to explain how, or I mean, this is not complete yet, but the goal is to make this equality manifest. So in some sense, make it a tautology. Is there a way to rewrite the left-hand side so that it really becomes like the right-hand side? And I'll try to just give you the broad idea, and I'll probably stop there. And let me skip this. So the idea is that the left-hand side, at least for weak coupling, for the perturbative when the lambda is small, which is the lamppost we are expanding around, is given in terms of sum over world sheets. sum over Feynman graphs. The field theory amplitude is given in terms of sum over Feynman graphs, and I've tried to draw some very complex Feynman graph here, which so there are these dots. It can go inside and do many complicated things. And the statement is that that is somehow equal to the sum over the world sheets. So this is what I meant at the beginning, that how can you transform something which is given in terms of world lines into something in terms of world sheets? And this turns out that there's a very natural way you can associate to each Feynman graph a particular world sheet. And this arises in a way from this open-closed string duality, that there's a way to glue together the strips of the Feynman diagrams to give you this closed string. And this utilizes certain mathematics of what is called the Strebel differentials, Strebel parametrization of the moduli space, and it refines an old ideas of Toft to associate how you can associate genus G world sheet to a Feynman diagram. So it kind of, the Feynman diagram is built up, and I'll just give you a picture here. This is sort of an example of a complicated Feynman diagram correlator, a Feynman diagram contribution to a correlator. And all these lines over here, these are the usual world lines of the field theory. I've drawn them as double lines because that's a very natural thing to do when you have a UN gauge theory, because these are like matrices and the two sides represent the two different matrix indices. And there's a natural way to represent the Feynman diagrams in this way. And you can kind of glue all these strips together to make various quadrilaterals in a natural way, which using the mathematics of this so-called Strebel differential. So you start with these so-called ribbon graphs, you can glue them up together to form effectively conformally strips. Each of these quadrilaterals is essentially like one of these infinite strips over here. It's just conformally equivalent to that. You can think of these ends going to infinity, then the strip essentially becomes like one of these quadrilaterals. So these are like the infinities, or more technically poles on the Riemann surface. And so you can glue up this Riemann surface into the so-called Strebel surface. So that's how you associate as a way. You have to just take it from me as a way in which you can associate to each Feynman graph a closed world sheet. And using this, and I'll just maybe just won't go much into the details, but using this, we recently worked on the tensionless limit of the ADS-CFT correspondence in 3 dimensions, and we've begun to make some progress even for the ADS-5 4-dimensional ADS. But in the 3-dimensional case, we understand very well this dictionary, at least in the limit which corresponds to that lamppost that we mentioned. And similarly, the tensionless worldsheet theory or the free super Yang-Mills theory, we have made some progress on. And we have even some proposals for what the dual worldsheet description is. We were able to match the spectrum and also make this equality of correlators that I mentioned more manifest. So I won't go into more of the technical details because I think it's already late. So this is all quite technical. So let me just close by saying that deriving gauge string duality, I think, can really overhaul our understanding of quantum field theory and quantum gravity. There are some test cases where this general program of reassembling field theories into string theories has begun to be explicitly carried out. And in that case, you could kind of go from the strings to fields and fields to strings. So kind of a nice picture in terms of discrete string bits that emerges, which I couldn't explain to you. And this holds out the hope that we can use this program to generalize to general large N quantum field theories and hopefully go away from this particular point, this free point or perturbative point. We have recently generalized this to matrix models where this which was one of the first large N field theories to be understood better. There are interesting twistor world sheet string theories that come in this construction, and an underlying topological string description, all of which I can't explain. There's also interesting connections to arithmetic through number theory, through this treble dictionary, but so many interesting things. But as I promised, let me end with this quote from Dirac, which I like. So he gave some lectures actually in Bombay in India in 1955, much before string theory was imagined. And he had this idea to try to go back to the Faraday lines of force. And he says one possibility in this direction of understanding and the electrodynamics sort of from this flux point of view is to think of the electron as the end of a single Faraday line of force. And the electric field in this picture comes from discrete Faraday lines of force, which are to be treated as physical things like strings. And so he uses that word. And when one has to develop a dynamics for such a string-like structure and quantize it, and then he says, in such a theory, a bare electron would be inconceivable, since one cannot imagine the end of a piece of a string without having the string itself. So he was basically saying that you really are forced to think of a string when you are thinking of even a gauge theory like electrodynamics with the electron and the photon. So I think that shows a certain very strong intuition and prescience from someone like Dirac. And so maybe we can realize that vision sometime in the future. Thank you very much.
Thank you very much. It was a really nice talk.
Thank you.
Very nice way to start the seminar. If somebody has any question?
Yes, I have a question.
Yes.
The quantum field theories in the boundary, there are always in Minkowski space. There are always have to be plane.
They need not. I mean, a quantum field theory can be. I mean, most good quantum field theories can be considered either in Minkowski spacetime or on even a Euclidean spacetime with the Euclidean signature. There is most good quantum field theories have well-defined analytic continuations to Euclidean space or vice versa. So these conformal field theories here can be considered, for some reasons, it's for some purposes, it's more useful or even simpler to consider them in Euclidean space. And that's more or less what I have done for many of the correlators. But in principle, you can use those to rotate to Minkowski space, though there are sometimes some very interesting subtleties about the analytic continuation. Was that your question about Minkowski versus Euclidean, or?
I was thinking about if it's possible to think in the future about quantum field theories in curved space. Like
in curved spacetimes also, yes, you can do that too. I mean, a quantum field in this ADS-CFT correspondence, you can generalize it to the cases where the boundary is not just flat spacetime, but curved spacetime as well. Yeah, no, that's also, that is not such a big generalization.
I think actually maybe what he meant was to have this duality, but not in anti-de Sitter, but maybe.
Yeah, I was thinking in that, for example,
Yeah.
because like we have this duality in ADS, and I understood ADS in the boundaries are plane, and
yeah. You can consider ADS which have boundaries which are not necessarily plane, or you can consider sometimes what are called orbifolds of ADS, or you can consider sort of, yeah, so there are, in fact, in ADS, three-dimensional ADS, the boundary in the Euclidean ADS3, you can consider boundaries which are almost any Riemann surface. Because you can kind of fill in a Riemann surface with a hyperbolic metric. So many boundaries, you can kind of fill the interior with hyperbolic metric. So you do not, so that by itself is not a big obstacle, but you can still ask, can you describe how much more general space-time geometries in the bulk can you describe? We understand asymptotically anti-de Sitter space-time and some cousins of those fairly well. There are maybe some other interesting generalizations in lower dimensions involving the so-called linear dilaton background, etc. But that is one of the ideas that you will be able to, by deriving this gauge string duality, try to consider a whole range of other space-times or string backgrounds where you can have a similar holographic duality. But you would really, many people are trying to think about how you can generalize to de Sitter space or even just quantum gravity in flat space-time. Asymptotically flat space.
Okay.
But that's still work in, it's not as well understood as an anti-de Sitter spacetimes.
Is there any other question? Comment?
Yes, I'd like to ask a question.
Sure.
So at the beginning, somebody asked if the gauge transformations in the CFT side correspond to something in the gravitational side. So this is also about that.
Yes.
So in Yang-Mills, we also have the so-called large gauge transformations, right? Which do actually do something non-trivial, which is that they change the winding number.
Yes.
So my question is, do these transformations correspond to something in the gravitational side?
Yes, very good question. I mean, the large gauge transformations take you from one vacuum to another, and the actual vacuum, in the quantum theory is are labeled by the so-called theta vacua, which kind of are a linear superposition of all the vacua with definite winding number. So the one you have to consider the sort of superposition of these to be the physical vacuum. I mean, there's a whole family of vacua which are labeled by this parameter theta, which is dual to the winding number. This theta is the thing which appears in the Yang-Mills theory, also multiplying this topological quantity F wedge F and the second Chern class. On the dual side as well, you can turn on the same parameter corresponding to this theta, and that is a field, something called the axion field in the string theory, and corresponding to the instantons of the gauge theory, which take you between different vacua. You have so-called d instantons of the string theory side. So indeed, those things are reflected very precisely on both sides.
I see. Thank you.
There is another question in the chat, but it says, thank you, Professor Gopakumar. I have a little question. Are there some perspective to study a duality with the Sitter space-time?
Yes, there have been some attempts. De Sitter space-time is a little bit the opposite of anti-de Sitter space-time. It is also it has positive curvature. In fact, it was de Sitter space-time that was discovered first and is probably relevant to our universe. Unlike anti-de Sitter space-time, in which the boundary is time-like, I drew the time direction and the vertical axis of the cylinder, and so the boundary is in the time-like direction. In de Sitter space-time, the boundary is space-like, and so it's sort of at the beginning or the end, if you wish. And so then it's difficult to make an identification. I mean, in physics or in the ATS-CFT, we, as I said, there's a Hilbert space, and the time evolution is the same. It's this, but along the vertical axis of the cylinder, both the bulk and the boundary. But for de Sitter spacetime, if you have the boundary is space-like, so there's no time on the boundary. So how do you interpret, even if you have a field theory on that boundary, how does it holographically capture the dynamics in the de Sitter spacetime? So this is a big puzzle, and there have been proposals about having that you consider something, the partition function of the field theory on the boundary gives you the wave functional at a given time on that space-like slice. And then you have to apply some, I mean, so it tells you some things about correlation functions of the de Sitter spacetime, but it is still not at a very good level of understanding. We don't have any case where there's really a microscopic description of well-defined quantum field theory, which captures some interesting things about de Sitter. So it's ongoing. There have been many attempts, but nothing fully satisfactory is, I think, the fair conclusion.
Hello.
Yes.
I have a question. Maybe this question comes from a misconception, but I thought that in the case of Maldacena, the super-Jamil theory is defined on the brain. And if that is the case, I don't see how to see the brain also as the boundary of the space, or is it the brain also the boundary of the space? I'm a bit confused about that.
Yeah. No, it's a good question to ask. Naively, yes. From what I told you, it would seem that the brain is just some defect in the space-time. So what Maldacena did was a very clever thing, that he considered a certain, not just the full D-brane geometry and the geometry surrounding it, he took a certain limit, a so-called near horizon limit of the brain geometry. So which kind of makes you zoom in on the geometry and go very close to the D-brane. And it is in that limit that you find that on the one hand, the brain is sort of the boundary of that region, which is enclosing a kind of a bubble of anti-de Sitter spacetime. So it's because of taking this limit that you are now the brain effectively behaves like the boundary of that of the spacetime that you are considering. It takes a little getting used to this, but it's sort of how it works in the near horizon region in some ways. It's there is, when you go zoom in on this brain in a particular way, you take a certain scaling limit. All the asymptotically flat part of the space-time goes away, and you kind of zoom in on this bubble inside the brain, or which is sort of trapped in the near horizon region of the brain. That is the anti-de Sitter space-time.
Thank you.
Since Maldacena has been mentioned so many times, I want to make the announcement that he will be giving a seminar maybe by the end of this year.
Oh, great.
Is there any other question?
Sir, string theory we basically do in flat space, huh? Minkowski space only.
That is the simplest case, which is mostly studied when people introduce string theory. But in principle, string theory can be defined on a large class of spacetimes, including an anti-de Sitter spacetimes of different kind. Typically, you need ADS5 times a 5-dimensional sphere, or ADS4 times some other internal spacetime, etc. So you can consider string theory on a more general class of backgrounds.
Can it be made independent of background?
When you say can it be made, meaning that can you have a description of the theory which does not refer to a particular background?
That will contain a journal means gene, mean I can treat it
Yeah,
gene,
yeah.
as a coordinate there.
It doesn't quite work like that in the sense that at least, okay, so there is a formulation of string theory in terms of what's called closed string field theory, in which the background, in which you think of something called the string field, which includes the graviton as one of its fields, and together with many other excitations, because in string theory, the graviton is the massless excitation, and there are many other massive excitations as well. And there's a string field you can define, which captures all of these. And that string field need not take the background value of that metric, need not be something fixed. And you can write down an action for that string field and equations of motion for that. That is the closest to, so to say, a background independent description.
Professor Gopakumar. So I have another question. So you mentioned like the extension to the de Sitter space is pretty like prohibited because of the space-like nature of the boundary. But as you mentioned, like there are a few like a QFD, it is pretty much Euclidean signature. So it should carry out even if the boundary is space-like, right? I'm confused by this.
Yeah, yeah. So at the one hand, it might seem that you can, I mean, in anti-de Sitter spacetime, when you consider the Euclidean boundary, you're still you're looking at the you can think of starting with Minkowskian spacetime, doing the analytic continuation. Then what you get is a in the Euclidean case is a hyperbolic ball, like a solid ball. I mean, in the Minkowski spacetime, it was like a solid cylinder, but in Euclidean spacetime, it's like a solid ball, like the inside of a football. And the boundary is a sphere, which is the surface of the football. But when you go to de Sitter spacetime, that has positive curvature. So the spacetime itself in Euclidean signature is like a sphere. It's not a ball, it's a sphere. And a sphere has no boundary. So in Euclidean signature, in de Sitter spacetime, is also very different from the Euclidean signature of anti-de Sitter spacetime. So, so that's one way to sort of answer your confusion. But ultimately, even though I use the Euclidean signature as a kind of a way to motivate, I mean, as a way to calculate, as a simplification in calculation, ultimately, if you have to think of the equivalence of the two theories, you need an equivalence of the Hilbert spaces, the equivalence of states. And that is there in the Minkowski theory. And then you have a Hamiltonian, which evolves the states up in time. And in the de Sitter spacetime, that's the part which is confusing, because you don't have a notion of a Hamiltonian evolution for the boundary. So that's where the confusion is. But it may just be that we are asking the wrong question in the de Sitter spacetime. It's not impossible. So I wouldn't say that. It's just that I think we haven't hit upon the right formulation. So that's a scope for all of you to think about and maybe come up with a good way to think about it and formulate it.
All right, thanks. Thanks.
Welcome.
A small conclusion? Yes.
Is anybody asking anything?
Yeah, but if you want, you can go first.
Okay. So my question is the following. When you were talking about deriving the correspondence, you showed that that equality between the correlator on the CFT side and the correlator on the string side.
Yes.
And the correlator on the string side is on shell. So it's a scattering amplitude. And we know that these can be computed in string theory. We know how to do it in principle, but off-shell correlators in string theory are a lot more complicated.
Correct.
Right. So my question is the correspondence, does the correspondence only involve on-shell string correlators, or do the off-shell correlators also have a part to play?
We think that there is nothing, any physical quantity in the string theory should map to a physical quantity in the gauge theory, any physical observables. Scattering amplitudes are a very large class of physical observables, which correspond to on-shell amplitudes, as you said. And those are the ones that match to these correlators. Just simple off-shell correlators typically are not physical objects in a theory of gravity or in the string field theory. So those are in some sense like gauge dependent, or they are not corresponding to a physical quantity. So those do not have any correspondence as far as we know. Just like gauge non-invariant quantities in the field theory do not seem to correspond to anything in the string theory. So in a sense, it is only for the gauge invariant observables on both sides that there's a connection. And on the string theory side, those typically correspond to on-shell observables. On the field theory side, those are the gauge invariant observables.
Thank you.
Welcome.
Okay, so I have a question regarding the last part. When you mentioned that there is this kind of recipe of mapping Feynman diagrams to worksheets.
Yes.
At the end, you also mentioned that this was like a work in progress to do it in the Gaussian unitary ensemble, right? But I get like a little bit confused because as far as I know, and I don't know if I'm quite wrong, when you want to compute some kind of observable correlation functions in the GOE, you have to, there are trace of Hermitian operators, and you sum over the fat graphs. And that sum in the large n limit, that is the argument of Hoff, gives you already like a surface version of the amplitudes. So what is the exact point that you want to that you mentioned that was trying to like take that wave mapping scattering amplitudes, but now in the GOE?
Yeah, so indeed, it has been known for 40 years that the Feynman diagrams of the random, this GOE or the summation matrix model give rise to these fat graphs, which kind of you can associate a surface to them. But that's as a picture. You can draw triangles and you can think of it as tiling a surface. The statement is that and in fact, people felt that that's actually only giving you a discrete version of a surface. So people actually looked not at the free Gaussian theory, but they added a potential term, like a quartic term, and then they typically took what's called a double scaling limit, where they went towards a critical point where the number of graphs that contribute to the free energy grows in such a way that it gives you a very fine tiling or a very smooth triangulation of the surface. And then they said, yes, that is the limit in which you can have a dual string theory. People did study the dual string theory in those cases, which was some kind of a two-dimensional or 1 plus epsilon dimensional kind of string theories. What we are saying now is that you don't need to take the double scaling limit. that picture of a triangulation you can make precise using the Strebel differential or this sort of a Strebel parametrization of moduli space. You associate a particular point in the moduli space of Riemann surfaces, and the sum over the Feynman graphs gives you sum over specific points on the Riemann surfaces, or moduli space of Riemann surfaces. And those also define a well-defined string theory, even though at first sight you might think, oh, you're only summing over some specific points. But really, that seems to define a well-defined topological string theory, which we have made a proposal for a sort of an A model topological string theory and a B model topological string theory, which is dual to the matrix model without any double scaling limit. So the claim is that there is a specific topological string theory which you can give an explicit description for, and for which you can even try to derive this duality, meaning you can see how this dictionary between Feynman diagrams and worldsheets, a precise mathematical dictionary, can be used to try to derive the worldsheet correlator of that of the other side, starting from the Feynman diagrams of the matrix model.
Oh, okay. Thanks.
Maybe it's worth it to mention that you have some lectures on YouTube about these Strebel differentials, which people can go and check.
I think like the Jerusalem Winter School lectures, maybe.
Yeah, that one.
Yeah.
So if somebody is more interested in more detail, then they can go to YouTube and check for those.
There's one work in one paper out with Edward Mazenk already, and there will be hopefully a few more. Daniel is also working on some aspects of this, and so.
Yes, there's a lot of things to do. Is there any other question?
Okay, I guess people have stayed for nearly 2 hours. It's a long time.
Yes, I think people is already tired. Okay, if there's no any other question, then let's thank again Professor Gopakumar. Thank you very much for this nice talk and for answer all the questions.
Yeah, welcome. Thank you.
And see you everyone in maybe next week in the next seminar.